you got this worksheet. I'm going to leave question 1 to you. Define an acid and a base according to Arrhenius. That's on the slides. Write a balanced chemical equation to represent the neutralization of nitric acid, that's HNO3, nitric acid with sodium hydroxide. And I'm going to just do one real quickly. So we've got nitric acid plus NaOH. And I said that an acid plus a base yields a salt plus water. So I can come right on over here. I got water. And where am I getting the water from? This H is reacting with that OH. The H and OH are neutralizing one another. HNO3 is an acid. It's a strong acid. NaOH is a strong base. You mix the two of them together and you can get a neutral solution. If you have the exact balance of acid and base, you can get a neutral solution. So what is the salt? You help me. What is the salt that's going to form when nitric acid reacts with sodium hydroxide? Sodium nitrate. So you're taking the positive ion from the salt, the negative ion from the acid, and forming the salt. Sodium nitrate. And that actually is balanced right there. I'll leave B for you to do. That should balance out real easily. Go ahead and do B right now. What's the salt? Gene? And what's the name of that? What is the name of it?
Ammonium chloride.
Ammonium chloride. That's the ammonium ion, and that's the chloride ion, ammonium chloride. And I mean, if we were looking at all of these would have AQs after them. There's not all of them. The water would actually have an L after it. But these are all AQs. They're all aqueous solutions. Okay, now I'll just do this one real quickly. This is sulfuric acid. Now, I didn't get into the Newton homeworks. And if you got into this sort of thing in the Newton homeworks, it could be a little more complicated. These are monoprotic acids. Monoprotic. Protic meaning proton. There's only one proton on that acid, HCl. Every HCl has just one proton. But this is a diprotic acid, sulfuric acid, H2SO4. It actually has 2 protons. So it's going to form water, and it's going to form potassium sulfate. What's the formula of potassium sulfate? Okay, this at the end of the semester here, you have to start wrapping your mind around everything you've learned. The potassium has what charge? Positive what? +1. And the sulfate has what charge? -2. So potassium sulfate is going to be K2SO4. It's going to take 2 of these to react with 1 H2SO4. And how many water molecules will that produce? 2. Okay? So it's still the same kind of game. The same game's going on. A proton is binding to a hydroxide to form a water molecule. But this thing has two of those protons. Two of those protons. So one of these with one of those gets you one water molecule. The second one of these with the second one of those gets you the second water molecule. All right. And these are just the standard equations. These are the three equations. I'm trying to write a 14 there. All right. You all right with all that? Okay, let's look at problem 4. 4A, B, and C are one type of problem, so I'm going to put a circle around those. That's one type of problem. And D and E is a second type of problem. Why are they different? They're different because here you're given a concentration of an acid solution. In D and E, you're given the concentration of a base solution. So you have to, it says there, careful, this is a base. So you have to be careful. So let's read what it's telling you here. Find the pH. Find the pH of the following solutions given their molarities. These are all either strong acids or strong bases, and therefore dissociate 100%. So what the problem giving you here, saying this is just saying the same thing twice. It's a strong acid. It dissociates 100%. That's what we've defined a strong acid as, right? Strong, it completely dissociates. Weak, it only partially dissociates. So, how does that help you? Let's take one at a time. Part A. We've got a solution that's 1.6 times 10 to the minus 2 molar hydrochloric acid. So what that means, I wish I had put myself a few more spaces here. When hydrochloric acid dissociates, if it is 1.6 times 10 to the minus 2 molar, it's 1.6 times 10 to the minus 2 moles of HCl per liter of solution. Every one of these gives you one of those. That 100%. It dissociates 100%. So every HCl, one HCl, gives you one H plus. Or H3O plus. Right? So if it starts out as 1.6 moles of HCl per liter of solution, it's going to end up, let me spread these out a little bit. It's going to end up with 1.6 times 10 to the minus 2 molar hydrogen ion per liter of solution, and 1.6 times 10 to the minus 2 moles of chloride ion per liter of solution. You see that? It's going to have the same concentration of the ions as it does of the molecules, because every molecule gives one of those. So what does that mean? That means you know this. Okay? For that problem, You know this. Keep in mind that an H plus and an H3O plus, I mean, if this looks better to you, if you like it better that way, I'll write it that way. We got an HCl going in the water. What happens? It dissociates, the proton goes onto the water, and the chloride floats around as a chloride ion. So you know this, and you want to calculate this. So the pH is going to equal the log of 1.6 times 10 to the minus 2. So now, go ahead and do that. Get out your calculator. My calculator gives me 1.795880017. I'll round that off to 1.80. Or 1.8. Either one. I should have given you this concentration to 3 significant figures. 1.60. Okay, go ahead and do B. Any question on A? Okay, go ahead and calculate B. Let me look at some people's answers. Oh, I see. That's it up there. You did the next one too, right? Okay, that's it. Yeah, that's right. What do you have? Where's your answer? Yeah, that's good. Got an answer? Yep. Got an answer? Yes.
I rounded it.
Mm-hmm. That's good. Yeah, that's good. How you doing? Let's see how to do it on yours. Clear this. So, where's your log key?
Right here.
Okay, and where's your EE key? Do you have an EE key?
No.
Which key would you use? What is this? This is a TI-30. Look, that's a TI-30. Why do you keep changing things? Where is your EE key? You can't even find it. I must be looking past it. How about scientific key? Like when you want to do 10 to the 10 to a power?
Second and then log.
Okay. So you're going to have this concentration, 2.7 e to the -4. So let's see, 2.7. second. I don't know how to do that. Man, I'll tell you, I don't get this. We got to work yours out, okay? Because I can't even figure out how to do it on your calculator.
I usually just do it the way you told us not to do it. Just type them in like this.
Okay.
Stop there. Be careful. I didn't want that.
How to do it.
I gotta pull down.
Yeah, wait. Okay, you could do a negative here. -4. Okay, now hit log of that. Hit the log of that. Okay, now you got to put that in there. Put 2.7. No, 2.7. 10 into the -4. It's complicated, isn't it? 10 to the -4. Now don't hit enter yet. Put a 4. Now close the parentheses. Now let's close. Now hit enter. Okay. I'll tell you what. KK, we're going to have to work on that. And if you want to borrow one of these, you can. Okay. Let me show you how to do it on here. See, it has a log key and it has an EE key.
Yeah.
So type in 2.7.
Clear this?
Yeah, clear that. 2.7. And then type EE 4. Okay, now change the sign. See, it's a -4. Now hit log. And there's the answer. Now, that's not the answer. Now you have to take the negative of that number. You see it's coming out negative, so you got to make it a positive.
Okay.
All right. Well, why don't you work with that one?
I'm sorry. Is that what if you rounded up to 3 point?
Yeah, 3.6, 3.56. Okay. So we got here maybe about a 3.6.
Yes.
pH of 3.6. All right. If you still are in trouble with your calculator, you got to solve that. Okay? You got to get to the point where you're getting these answers.
I can't be all the same.
Yeah, KK's got a TI 30 back here. You got it. Well, you have to figure out how you're doing this. I couldn't even figure out how to do it.
Me too.
What? This
I can know how to put negative on my log.
Log?
You have the same calculator, right?
Yeah, this one?
Okay, well, I'll tell you what. Yeah, work on that. Because it's not a trivial matter to get the right answer out of these calculators. I work with 2 different calculators, but I'm having trouble figuring out how to do it on their
I can't
calculator.
make the log negative, so
All right,
I just have to know that it's possible.
let's go on to E. I'm going to choose E because it got a little bit more room to solve the problem underneath it than I do D.
Make my pencil.
Okay, now this says, careful, this is a base. The biggest problem students have on this kind of problem is they look at this and they go right ahead and do pH equals in the negative log and they figure out a pH, but they don't have the hydronium ion concentration. So let's see what's going on here. We got KOH, and if we put that in water, we get a potassium ion and a hydroxide ion. And we're being given 2 pieces of information. One is that it's 3.73 times 10 to the minus 2 molar potassium hydroxide, and that it is a strong base, meaning it dissociates 100%. So just like the strong acids, every one of these breaks up into one of these and one of these. It dissociates 100%. So there's none of this left in solution. It has all become potassium ions and hydroxide ions floating around in the solution. So we're going to get 3.73 times 10 to the minus 2 molar hydroxide ion. Now there's two ways of doing this problem. I think I will just go down one road. We'll go down the POH road. POH. This is the hydroxide ion. So the POH, not the pH, the POH is equal to the negative, the log of the OH ion concentration. So let's get the POH, and then let's figure out what to do with that. Okay, but let's get that far. So on your calculators, okay, Kay, do you want to use my calculator or your calculator?
Well, I know both now.
You know both?
Yeah.
Can you do it on that?
Yeah.
Sure? Okay. And, well, maybe after class, show me how to do it on your calculator. Okay, so we put in the 3.73. So I'm getting that the POH is 1.4 or 1.43. See, we've got three significant figures here. So we'll say the POH equals 1.43. Okay? Everybody with me there? Okay, now what can we do with that? The question up here, remember the question up here is find the pH of this solution. It didn't say find the POH, it said find the pH of the solution. So, pH plus POH equals 14. So the pH equals 14 minus the POH. On the exam, I'm not going to get too persnickety about significant figures on pHs and POHs and all that sort of thing. If you are using these equations properly, and you're 3.57 or 3.6, don't sweat over those things. I
You
will.
have to remember like the pH and then the HO3 and KW. You're not going to give that to him.
The formula?
Yeah, you have to remember those. You got those written. I've got them there. You need to know that pH equals the negative the log of the hydronium ion concentration, and that the hydronium ion concentration equals 10 to the minus the pH. Okay, this we may have just mentioned that on last Thursday. This is coming out of, it's coming right out of this equation right here. Oh, come on, go away. Thank you. It's coming out of this equation right here. That the Kw is the hydronium ion concentration times the hydroxide ion concentration equals this 10 to the minus 14th. If we take the negative, the log of 10 to the minus 14th, it's 14. The negative log of that number is 14. That's where that 14 is coming from. Okay? So I didn't just pull that out of thin air. It's coming out of this equation. But now we're putting everything in logarithmic terms, not just what those actual numbers are, but what are the logs of those.
Remembering that, we can just remember pH plus POH.
Yeah, I think so. I think so. The other route to solving this problem is going from this equation. It's a little, that's another way of doing it, but I'm not going to dig into both ways of doing it. Just know one way of doing it. At least know one way of doing it. If you're dealing with a strong base, just remember when you see a strong base and you come over here and you go, I got 3.73 times 10 to the minus 2 molar, what? It's hydroxide ion. It's not the hydronium ion. It's the hydroxide ion. So you can't just take the negative, the log of that and say, oh, that's a pH. It isn't. It's a POH. Follow me? Okay. So we're kind of going down through types of problems. So number 5, question 5, gets you to another type of problem. If you know the pH, then the hydronium ion concentration is this. So you could just put this equation up here. That's the equation you're using to solve question number 5. What is the hydronium ion concentration? What is the hydronium ion concentration? That's your unknown. Okay, now here's where you use your 10 to the x key, and it's usually a secondary function on the calculator, but find that function on your calculator. It's usually right above the log key because it is the antilog. That's what that is. It's the opposite of the log. And that's why they usually put those two functions right on the same key. And I'm getting that it equals the hydronium ion concentration here equals 3.72 times 10 to the minus 11 molar. That's the complete answer.
Okay, so how do you do that on a TI-30?
What?
How do you do that on a TI-30?
I thought you had it.
I didn't. I don't have it now.
It was like second.
Okay, here, type in 10 to 10.43.
10.43.
Now change it to negative.
Negative.
Second, 10 to the x.
There we go.
There you go, okay? So you got to change it to a negative.
Oh, yeah. Okay.
You got to change it to a negative.
There we go.
Is everybody getting that on their calculator? T?
Sure.
You got it? Okay, and then put molar after it. Capital M. So it's saying, what is that concentration? It's in molarity. Okay? Good. You got it? No, this is 3.72. Look at. Okay, I'll tell you what you did. I think I know what you did. Type in, clear it. Clear your calculator. Can't you just clear? Okay. Okay, now type in 10.43. 10.43. Change it to a negative. What did you do? Hit that? Okay. Now hit second. Log. Okay. I don't know. Let me see here. 10.43 negative. No? KK, did you get it?
Yes.
Okay. How'd you do it?
I'll have to put negative to it. Oh, yeah. All right.
Okay, you got it. Okay. See, you didn't put the negative.
Yeah,
and that's why you got 10 to the 10th. It's 10 to the minus 11th.
I think I'm doing it. But like all these answers like 0 to 0. Like I did 10 to the negative 7.
Yeah.
It's like 0 0 0 1.
Yeah, so you could convert that to 6.6 times 10 to the minus third.
Oh,
1,
okay.
2, 3.
Okay.
Okay, convert those over.
Okay.
All right. Well, let me run down through. Let me just go ahead and do them. Some of you done them all. I'll write these numbers up there real quickly.
It just means 1 times. So when you just have an E, that just means 10. So it'll be 1 times 10 to the negative 7. I don't get an E though. Because my E. Alright, so go back. So do your problem.
Okay, I'm going to try to get back over to our slides in a minute here. I want to look at titration and dilution. No. Have we already done that? We did dilution. Not titration. Okay, so we got to look at titration.
Whenever I ask them, like, okay, it gives me the temperature and then, like, the product.
At one of the
Like,
ion
how would I
product
get-
of water, what is the concentration of hydroxide ion at this temperature?
Like, is there a formula for that? Because I don't know how to get that.
The ion product,
Like, it's cold enough to wear it.
5.13.
I look like all summer. Wear this thing.
I think that,
Is that like a trick question? Or like
yeah. Oh, what is the concentration of hydroxide ion
Yeah.
at this temperature? Oh, man. That, is that on the quiz?
No, it's on the homework.
It's on the homework.
Quiz, there's a negative.
Yeah, well, all they're saying is that the ion product of water at room temperature is 1 times 10 to the minus 14th. They're giving you a different number at 100 degree at the boiling point of water. That is beyond the scope of what we talked about. Well beyond the scope of what I expect you to
Okay,
understand.
I was like, are you going to go over it? But
No, I'm not going to go over that.
Okay.
This where I say the 1 times 10 to the minus 14th, that's the ion product of water at room temperature.
okay, 1 time.
But they're saying here, if at the boiling point, that number changes, that the water has a different ion product. So that's well beyond the scope.
Okay.
Just remember 1 times 10 to the minus 14th for room temperature.
Okay.
And I don't know what to say about that question.
Okay.
I love the game. It's like one.
Okay. Okay, now let me just make a comment back here on problem number 4. I have not taught you how to solve this kind of problem for a weak acid or a weak base.
So it's not going to be on exam?
It won't be on the exam. Any one of these. This here only works because they dissociate 100%. If we did this with acetic acid, we couldn't just straightforward go through this.
So the only ones that are going to go on the exam are like these.
Right. It has to be a strong acid or a strong base for you to be able to calculate it. Can it be done? Yes, it can be done, but you have to know solubility constants and do other calculations before you can find out the hydronium ion concentration.
So are any on the exam going to be like workout problems? Like
Yes, yes.
Besides the multiple choice, or is it integrated with them?
Well, there will be some problems in the multiple choice. There will be some on the multiple choice. It says the pH of a solution is 5.75, something. For example, what is the hydronium ion concentration? And it'll give you 5 choices. So you will actually have to figure that out and then figure out which answer is the best answer. So there will be problems in among the multiple choice. You just don't have to show me your work. You just have to choose an answer. But on the other ones, the last 2 pages of the exam, you have to show me how you're getting your answer. And I will give partial credit. If you got the right equation, if you sat there and you got a big question mark, I don't know how to do this, but you know what equation applies, write it down. Write down the equation. If I at least know that you know where to get started, I will give you some credit. All right? So don't just leave it totally blank. You say, I don't know how to do this. Well, if you know the equation, write it down. If it's the ideal gas law, you know it's an ideal gas law problem, write down the ideal gas law. At least I know you know the first step to take in solving the problem. And if it's worth 3 points, I'll give you a point. Okay? You get it all set up, but you get the wrong answer, you get 2 points. You get it all set up and get the right answer, you get 3 points. So I'll give you partial credit. All right, so this only works with strong acids and strong bases. You have to take a different approach with weak acids and weak bases, and I won't give you weak acids and weak bases. Okay, now these are weak acids and weak bases. Complete the following acid dissociation equations. These are probably all, weak acids. Look at here. Here's water reacting with water. We'll get down to that one. But there's carbonic acid, H2CO3. That's what's bubbled into all the carbonated. You bubble CO2 into carbonated into beverages, and you carbonate them, and it forms this carbonic acid. So a proton is going to go on the water, and it's going to leave the bicarbonate ion floating around in there. So we're taking a proton off the H2CO3 and putting it on the water. Now here's hydrogen sulfide, which is really putrid gas, hydrogen sulfide gas. It's rotten egg smell, because that's what you're smelling. When you smell a rotten egg, it's hydrogen sulfide that's coming off of the egg as it's rotting. There's protein in there, there's cysteine amino acids, they have sulfurs on them, and as it decays, as bacteria decay the egg, it produces hydrogen sulfide gas. So take a proton off of the H2S, and then ask yourself, if I took a proton off of here, what would be left? I take an H off of there.
It'd just be sulfur, wouldn't it?
How many? I've only taken one H off. So you got one H left over and a sulfur left over. And what would its charge be? Negative. Why is it negative? Well, it lost an H plus. That's what it lost. It was neutral, and it lost an H plus. So now it's going to carry a negative charge. And notice over here, no charge, no charge. Plus 1 minus 1 balances out to 0. Okay, they are each charged, but they net out. The net charge on this side of the equation is 0. All right, so do C. Do C. What's left over? And what charge is on that? Negative. So that's the bromide ion floating around in the water. HBr dissociates into an H3O plus and a Br minus. And we've got these arrows going back and forth, meaning that there is an equilibrium here. When you saw when I wrote the HCl, I pretty much just, let's put the water in there. I just put an arrow going to the right. It's 100% dissociated. All right? So when you see just an arrow, that's not an equilibrium. It's proceeding from reactants. Reactants are becoming products, period. But here, where you see the arrows going in both directions, the reactants form products. The products can reform the reactants, and you have an equilibrium. You have a balance. You have all of this stuff floating around in the water when you have an equilibrium. All those things are present. Up here, the only thing present now is hydronium ion and chloride ion, and no HCl molecules. Okay, now problem 7 is titration. So hopefully I have these slides up here.
What is titration?
It sounds like a fundamental question. Which slide has titration? What is titration? Okay. Titration is a laboratory technique to determine the concentration of a solution. You usually know what the solution is. You don't know its concentration. Like you might know you have an HCl solution here, but you're scratching your head. I don't know if it's 1.5 molar or 0.1 molar hydrochloric acid, or 0.01 or 0.001. I don't know how concentrated this HCl is. So you would do a titration. It's a quantitative technique. You need to have a base of known concentration. So you're going to react a base with this unknown acid, and by knowing the concentration of the base and knowing a few other things as this titration experiment is set up, you can calculate your unknown concentration. So let me see what we got slide-wise. Yeah, here we go. Here we go. I like this slide better. The other one was an OpenStack slide. This one I got somewhere else, I think. So here's the situation. You could titrate a base into an acid, or you could titrate an acid into a base. You could work either way here, but let's take this case where we have let's say we have an HCl solution of unknown concentration. And so we are going to use a sodium hydroxide, a base solution of known concentration. So we would call this our standardized solution. We know its concentration. Oh, I should have I wish I'd brought the phenolphthalein in here and to kind of showed you this. The sodium hydroxide is water white. This looks like water. It's no color. It's clear, colorless. HCl, clear, colorless. And so you're dripping a clear colorless solution into a clear colorless solution. They're neutralizing each other, producing a clear colorless solution. You can't see what's going on, is the point. Okay? You can't see anything happening. So you put an indicator, an acid-base indicator, into the acid, which is clear and colorless in an acid, and it's bright pink in a base. So when the solution becomes basic, bam, it turns into this purple-pink color. It's an acid-base indicator. So it's going to stay clear and colorless until it's no longer acidic. And as soon as it stops being acidic, that's what you're starting with here. You're starting with an acid down here. And as soon as it is reverting to becoming basic, it changes colors. And that's when you stop the titration. Okay? So what if you wanted to imagine something in your mind, imagine you're on a board and you have a log underneath the board and you're balancing. Okay, don't worry about it. if you wanted an image to think about, you got this balance, you got this solution that could be acidic or basic, and you're trying to find out the point. Let me see if I can draw. You're trying to find the point where this person is perfectly balanced. It's not tipping this way, it's not tipping that way. It's neutral. So I'm trying to give you a physical image of a neutral solution. pH 7. It's not tipping towards the acid side, it's not tipping towards the base side. Perfectly neutral. Won't stay there very long. You put one more drop of base in there and it's out of balance. You follow me? Bam, it's gone over to be basic. You don't want that. You want to stop the titration when it reaches that perfect neutral point. And so you don't keep titrating to get a brighter and brighter and prettier color. This is getting more basic. Follow me? All right, why is that? That's your equivalence point. That's the point. You're starting here with a certain amount of hydronium ion in the flask. So at the start, you have hydronium ion. You have a certain concentration of hydronium ion in the flask. And you are going to drip into this flask base until you get an equal amount. So you're going to drip this in until you get an equal amount of hydroxide ion has dripped into the flask. With me, Gene? Yes? Just nod your head. Yeah. No. You got it? All right, so that's your equivalence point. So now, before we'll get to this equation, but remember this equation. Molarity times volume in liters equals moles. So what this equation is basically saying, at the equivalence point, the moles of hydronium ion equals the moles of hydroxide ion at that equivalence point. And so what are the moles of the hydronium ion? It's the molarity of the acid times the volume of the acid. What are the moles of the hydroxide ion? It's the molarity of the base times the volume of the base. Molarity times volume equals moles. So how does that help you? Well, the way that helps you is that the way you start this equation, this titration right here, is you put a known volume of acid in the flask. So volume of the acid is known. The sodium hydroxide solution, the molarity of the base is known. The volume of the base, that's why you're working in a burette. A burette is calibrated from 0 down to 50 milliliters. You can get different size burettes, but we use 50 milliliter burettes usually. You can get 10 other molarity ones. But you start at 0 and you drip it in, and then when it gets to that equivalence point, you're able to figure out how much base I put in there. And what is unknown? The molarity of the acid is unknown. So where does that get you? That gets you from an equation that has 4 factors in it. You know this, you know this, you know this. By the way you have constructed the titration analytical technique, you do it so that you know what you're starting with in the volume of the acid. You know you've standardized the base. You know how much base it took to neutralize. And that amount of acid, you pipette in 10 milliliters of acid, exact volume of acid gets put into the flask, and then you're able to calculate the molarity of the acid. So here, let's look at this. Molarity of the acid times the volume of the acid. Volume of the acid equals the molarity of the base times the volume of the base. Okay, now rearrange that equation while I plug in, finish that equation. Molarity of the acid equals what? So you have to divide both sides by VA. So this is going to be the molarity of the base times the volume of the base over the volume of the acid. Now this is the scenario where we're working with a unknown acid concentration. We might know it's HCl, we might know it's nitric acid, sulfuric acid, whatever it is. We know the acid. We don't know its concentration. That's what we're trying to figure out, is its concentration. So we have to get a standardized base. So let's get an example. Suppose we could go back to the worksheet right here. What happened? Hang on a second. Well, that's a good problem. I just want to see if we have another one. Yeah, here's a picture of it. Here's actual photographs of it. Here, Mark, can you turn 2 of these lights out so we can see these colors a little bit more vibrantly? So here's your acid in your flask. It's clear and colorless. Your sodium hydroxide in the burette. There's your burette. And as you drip the acid into here, it actually does look kind of purple. They're probably using phenolphthalein here as the indicator. You drip this in and it turns purple, and then the purple color disappears. Why? Because, well, just temporarily, right where the base went in, it made that environment right around those drops basic, made the phenolphthalein turn purple, and then the acid came in and re-neutralized it, and it turns clear again. So this keeps happening over and over and over again until finally you add a drop of base and it turns purple, and the purple doesn't disappear. It stays purple, pinkish purple. And then you know you're at your end point, and that's when you stop. You don't add any more base, and that's when you read your burette. You read your burette here to figure out how much sodium hydroxide. You need to know what the burette reading was to begin with. Usually start at 0, and if it reads 27.8 milliliters, that's how much volume of base it took to neutralize that volume of acid. So let's see if we have a problem in here. Here's different acid-base indicators. Where's phenolphthalein? Right here. Phenolphthalein starts changing. You know, these different indicators can change at different pHs. Here's bromothionyl blue. It'll go from, I think here, colorless, then it turns yellow, and then green, and then it starts turning blue, and there's your endpoint. I think one reason why we like phenolphthalein is that there's no color, and then there's color. You know, it's kind of a go, no-go kind of decision. So phenolphthalein is a workhorse. It's the most common acid-base indicator. And then let's see here. I don't know how many of you have hydrangeas, and you think, oh boy, look at my neighbor, got a different color hydrangea. No, their soil is a different pH. These different colored hydrangeas are just due to the pH of the soil they're growing in. You put Miracle Grow on that soil, and they may, if the soil is basic or alkaline, you put Miracle Grow on there and your hydrangeas will change colors. Okay, let's see if we can get to an acid-base calculation. All right, calculate the molar concentration. Calculate the molar. I'm trying to find one with an acid. Okay, and let's assume this is let's assume that's that, and this is that. I'm just upping the significant figures on this. So here is a titration problem. Let's do this one, and you can do the one on the worksheet in just a second. If 28 milliliters of a 0.5000 molar sodium hydroxide solution were added to an unknown acetic acid solution, this is a bogus problem. It does not tell you the volume of the acetic acid.
It's missing. At least one number.
Would you use the moles over area equation for this then? Or no?
Yeah.
I think you would, because in the homework that's what it shows.
See, this is how Newton does it. They give you bogus questions like this.
We will, Shantae, this can't be solved because we got two unknowns here. We do not know this, and we do not know this.
So we can't do the equation.
So you can't calculate.
Lying to us again.
This is okay. Let's do a problem. Let's do a problem. Let's do that one, because what you'll see in here.
Are these the type of questions we'll see on the exam?
Yeah, you'll see a problem just like this on the exam.
Okay.
So let's read it, and then we're going to label this problem. Remember, we're working with this equation. We're working with this equation. So we want to read this problem and figure out which of these three of these four things are given in the equation. That's why I stopped. I can't sit down here. That's why I stopped abruptly reading that other one. There were only two of these. So let's read this. Calculate the molarity of the base solution. All right, that's what it's asking you to calculate. Calculate that. The molarity of the base solution in the titration reaction when 26 milliliters 26 milliliters of a 0.638 molar HCl solution is titrated to the equivalence point with 50 milliliters of KOH. So what's the 50 milliliters?
VB.
VB. All right, so now we know that MB is the unknown. So we want to rewrite this equation. MB is going to equal what? MA over VA divided by VB. Is that right? Okay, now, VA and VB are volumes. The most common problem I see students having is mixing those volumes up. So you don't just pick a volume out of this problem and punch it in here. This volume here goes with this acid there. You with me? All right, so pay close attention to what the volume is associated with. So we're going to have that molarity times that volume. All right, that's VA. VA is the 25.6 milliliters. And then VB is 50 milliliters. You can see that milliliters cross out, and the answer is going to be in molarity. And what is that? What? Is that right? Agreed? Not questioning you, Daniel. I just need confirmation.
Agreed.
Agreed. So that's how you do a titration problem. Read the problem carefully, word problems, figure out. Now you can see if you put 50 in the numerator and you put the 25.6 in the denominator, there's no way you're going to get that answer. Right? All right, so you got to get the volume, you got to know what the volume is associated with in these equations. Not a trivial matter. You don't have to convert these volumes into liters. I have told you that molarity times volume in liters equals moles. But here we are calculating molarity, and so whether you converted it into liters or left it in milliliters, you will get the same answer. Because milliliters will cross out with milliliters, liters will cross out with liters. So you can convert it to liters, but you don't have to. But let me just say this. There will be a problem on the test where it asks for moles, not a titration problem. But if you're working with solutions and the problem is ever asking for moles, then you do have to convert the volume into liters. All right? So, for example, I'll give you an example. You have a solution. You have an NaOH solution that is is 0.257 molar. How many moles of NaOH are in 35.5 milliliters of this solution? Okay? There's a problem that's asking you for moles. And so the molarity is going to be times the volume in liters equals moles. So you have to take your molarity times, convert that, 35.5 milliliters, how many liters?
0.355.
0.0.
0.0355.
and that's going to give you moles. All right, so if the question's ever asking you for moles, then you have to convert it to liters. But in titration problems, your phone can't take a picture of what used to be there? You need to get an upgrade.
Yeah.
It's coming. It's coming. That phone is coming. Apple's working on it. Okay. All right. Okay, Mark, you can turn the lights back on. We got a minute for other questions. Oxidation reduction, don't worry too much about it. Here's what I do want you.
Yeah, Apple can't do that.
I forgot what
Are you sure it gave you that one?
Are you familiar with this? At least know this much. Oxidation is loss.
Oh, okay.
Reduction is gain of what? Electrons. All right. We obviously didn't get to cover oxidation and reduction.
5 modules ago.
What?
We learned that like 5 modules.
Did we?
It was in Newton. We didn't do it in class.
Oh, okay. So that's a simple.
But you know how reliable.
But don't worry.
Is what?
I think I will be satisfied with you hearing those words and being a little bit familiar with what oxidation and reduction.
What's dilution again?
Okay, dilution uses a very similar equation to this. Dilution is where you have, let's say you have 12 molar hydrochloric acid, and you want to make a 5 molar HCl solution from it. And so what is dilution? M1V1 equals M2V2.
Okay.
Let's say you want to make 250 milliliters of a 5 molar HCl solution from this. And the question is, you know this is your beginning molarity. You know what you want to make. You know how much you want to make of it. What you don't know is how much of this concentrate should I take to make that solution. And so V1 equals M2 times V2 divided by M1. So that's going to be 5 times 250 milliliters divided by 12 molar. But see, you're stepping down the concentration of your concentrate. You can never make this more concentrated than that. The only thing you can do is add water to it and make it less concentrated. So V1 is always going to be less than this number, whatever it is. And then you add the rest of water to it, you got your solution. Okay, all right. I'm recommending you come in here at 7:45. You don't have to, but the exam will end at 9:25. Okay? So if you come at 9, you got 25 minutes. All right? Don't come at 9. Don't come at 9.
One of the problems when it said H2 plus H2, there's a dissociation with it. Once you do that, would it be H3O plus? And when it's HO, would it be switched to OH negative?
I'd have to see what you're talking about. Here's your homework from Module 10. Don't leave without your homework.
So this one, right?
Let me finish Joel's question.
So would it be that, but would that be switched to OH instead? Because that was the actual, that's the actual name.
Only because that's the way we usually.
You're right. So
Yeah.
it wouldn't be the usual right. Okay.
That'd
it
be
would
fine, but we
You
usually
want to have
see it.
switch it to
Right.
OH. Okay. That's
Yeah.
why I just wanted to know.
Yeah, yeah. It's just our
The proper
way
term.
we normally write it is OH.
Right there, did you see the
No, and I
I'm gonna have.
ask
I'm going to just have the gas laws.
But I went online and I just the gas.
Yeah. Folks, the gas laws will be on the back, but you do need to know the other formulas.
How could you?
pH, these other formulas?
Should we get a sheet of paper?
Yeah, you can. This is gas laws I talked about.
Is it okay if I take a picture of this because it needs to be separated?
Yeah. Yeah, I'll tell you what, let me look at it. These pretty quickly. This is right. The kinetics because of temperature.
And the problem, I wasn't sure how to do the problem here.
Okay, I'll set that up for you.
Okay. Oh, I can't believe I forgot that one.
Did you do this problem?
No.
So 12, you got 88. I mean, and it's Ashley.
Good luck on your microbiology.
Okay, now let me show you real quickly. The equation is that Q, or later on we'll talk about delta H. But just the amount of heat involved here is the mass times the specific heat times the change in temperature.
Okay.
All right, and so here's your mass. Here is your specific heat.
Okay.
And your change in temperature. It's in delta T is always the final minus the initial.
Okay.
So we're melting this from 25, that's initial, to 660.
Okay.
So just take 660 minus 25.
Okay.
Notice this is calories per gram degree centigrade. So you're going to have grams here times calories per gram degree centigrade times degrees centigrade.
Okay.
And the answer is going to come out in calories.
Calories. Okay.
And this problem is the same thing. You just have a different temperature change. You have 100 grams of solution, and you have a different specific heat.
Okay.
All right? All right.
All right. Thank you so much.
You're welcome.
So is this going to be on this test? The Boyle's Law?
Yeah, yes, yeah, and you did all of these? Let me take pictures of yours. I've been wanting...
There's no review for exam 3, just for the final, right?
Pardon me?
On Canvas,
There's no what?
review for exam 3, just for the final.
Yeah, let me see if you say you can't find one, you're probably right. Let me just take these and see if I can do some of these problems. That's neat. You did all these.
I didn't do the next one.
You didn't do the next one?
Well, just one.
I started bragging too soon. Huh?
Yeah.
Well, you did a bunch of them. That's good. And I mean, if there's 3 problems here, and you did 2 and you feel comfortable with them, you don't have to do them all. And then this is just temp pressure conversions. Okay?
Yeah, there's just final exam study guide and then final exam review.
Okay, let me go back, ma'am. I'll try to get back there and look those over and see if I can find something else.
Okay, thank you.
Yeah, you're welcome. I'm sorry, what's your name again?
Michelle.
Michelle. I wanted to see, I wanted to remember who did these in case I get to do them.